Part three.
Yeah, I think I have one for expressing it on it. Like all the
Oh,
ones.
we're coming to that. They may be out of. They may be out of.
Cool, okay.
All right, so I put another couple of questions, I think 4 questions on the unit on statistics. And we're going to talk a little bit about statistics this morning. I want to just hit or primarily work on one area of it. But well, we've already been playing with statistics without necessarily calling it that. And that's the probability that certain allele sets or certain genotypes can be inherited when we're doing a fork diagram or figuring out a Punnett square or figuring out the genotype ratios. Those are really probabilities. Those are the likelihood that a particular genotype will exist or a particular phenotype will exist. So with a little more formally, looking at what are some of the statistical rules or statistical manipulations that are actually taking place kind of behind the scenes. Of course, when we think about statistics and genetics, a lot of times people will think about predicting, like, will my child have this particular trait, or what's the likelihood of inheriting a particular phenotype of disease. And that's a big part of what genetic counselors will deal with and do the genetics behind the scenes to give those kinds of answers. Breeders also would be concerned with this because you're looking for a particular type of phenotype for the animal or plant that you're trying to develop. And pretty simply, we're always just looking at a probability, the number of times that something happens out of a total number of happenings, that you get a particular outcome, and you've got a large number of things. And so with genetics, you're usually looking at the number of events are organisms. They're meiotic events, or they are zygotic events, they're fertilizations, they're the number of organisms that you have observed and observed their phenotype, or that you might predict could occur. If you're thinking about something pretty simple, like the 2 sides of a coin, right? You have 2 choices. It can land on one side or the other. And so one side is a head, one side is a tail. Then you've got 1 head out of 2 possibilities, or 1 tail out of 2 possibilities. So the chances of being heads is a half. The chance of being tails is also a half. If you have a die that you know, playing Monopoly kind of thing, well, it has 6 sides, right? 1 through 6 on there. So what's the probability that it comes up with a 1? 1 out of 6. If you had 2 dice that you're playing, and you know, one could come up a 1, the other one could come up 6. What are the probabilities? Well, those 2 dice are rolling, theoretically, everything being fair, they're rolling independently of each other. Okay, so that's one of the types of interactions is to look at events that could happen, 2 independent events, or 3 independent events, or 18 independent events. If those events, if the likelihood of one thing happening has no influence at all on the likelihood of another event occurring, then we say they're independent. And for independent events, you would use what's known as the product rule to figure that out, figure out the overall probability. Sometimes things are independent and they're actually ordered, right? Like, you know, the first die is this, the second die is this, the third die is this, right? If you're rolling 3 dice. But what if you are thinking about the outcome of events when the actual order doesn't matter? Like if you had 4 dice, or what's that game, Yahtzee, right? You have 6 dice, right, or 5, whatever you have. Anyway, you got the idea. You roll the dice. What's the likelihood that all 6 of them come up 6s? Well, it's 1 6 times 1 6 times 1 6 times 1 6 times 1 6. 1 6 to the 6th power. But you might ask the question, what's the likelihood that any 4 out of the 6? Right? Now, it could be the first 4, it could be the last 4, it could be the first 2 and the last 2, right? There's multiple ways that you could get 4 things out of 6 events. So and it doesn't matter what order they roll, okay? So that requires a slight variation on the product rule called the binomial expansion. And that formula allows us to predict what's the likelihood of a particular type of event occurring multiple times and the order doesn't matter. Like what's the likelihood if you had a dog's had some puppies, they had 8 puppies, what's the likelihood that any 3 of the 8 had a certain phenotype, right? If you know what the probability is for that phenotype for one animal, now you can predict what is it for any 3 of them to have that phenotype. And then there are some instances where 2 events are in fact not independent of one another. They are mutually exclusive of one another. Like what's the probability of being Schrodinger's cat, right? Remember Schrodinger's cat? It's alive and dead, right? So what's the probability of being alive or dead? Nope. What's the probability of being alive or dead? 100%, or 1. They're mutually exclusive. You are either alive or you are dead. Okay, you can't be both at the same time. You can't be Schrodinger's cat.
What about being a coma?
You're alive. So when it's a mutually exclusive event like that, or 2 mutually exclusive events, the probability of them is going to add together. Okay, the probability for all the events occurring is always going to need to add to 1, because, or 100%. But we talk about probabilities, we talk about a number from 1 to 0. So with the sum rule, you're going to always know that you need to think about the sum rule when the question can be stated in a form that is a choice, this or that, right? Because you can't be both at the same time. So the question will always come about, the events you're concerned with will always be able to be stated as a choice, this or that, okay? And then you know, well, I've got to deal with the sum rule. And it's a less used rule. The more used rule is binomial expansion and the product rule. You have a question? So if the question asks any time, and you can express it in the form of this and that, right? And it can be more than one thing. It can be this and that, or that, or that, or that, or that, or that. Well, then you've got a choice, right? You don't have, you have not a choice. You have 2 simultaneous things. It could be green and tall, right? It could be any 2 things that could exist at the same time. So that would be indicated that you're going to use the product rule or perhaps the binomial expansion rule. So the occurrence of 2 independent events, you're going to multiply their individual probabilities. Okay, and so we've been doing that already with our fork diagrams. Okay, the fork diagram, to work it out, you're really just using the product rule. So you've already been using it. So here's an example. There's this phenotype called congenital analgesia. Basically, nerve endings don't either don't fire correctly or they aren't connected correctly. I don't know which it is, but anyway, you kind of don't feel pain, right? So if two individuals that are heterozygous, so they have this allele, they're normal. So that means they also have the normal allele, which is dominant. But they're going to have some kids, and they want to know what's the likelihood that, you know, we're going to have 3 kids. What's the likelihood that those 3 kids are going to have this disease? Or what's the likelihood that one of the kids would have the disease? What's the likelihood that the first 2 kids would have the disease? So if you're going to start asking questions like that, you're going to start needing to apply either the product rule or the binomial expansion rule. So first off, you know, it's a monohybrid cross, right? You've got these 2 parents, and you know, if they're going to cross with each other, here are the possible genotypes that could be formed. And of those genotypes, only one of them could actually result in the phenotype, the analgesic phenotype. So the probability that a child inherits that genotype is 1/4. And that's the probability for the phenotype as well. So we can say that the probability P for congenital analgesia is 1/4, 1/4, or 0.25. Usually is good when you're working with genetics problems. You're used to using 1/4 and 3/4 and 1/16 and things. So that's a fraction. You just think of it as a fraction now. And you can convert it to decimal if you want to. You don't need to. But what's the probability that 3 kids would have that phenotype? Well, if the probability for 1 kid is 1/4, the probability for the second kid is still 1/4. Just because you've had 1 kid doesn't mean that the other ones all have to be here, right? So the idea that a lot of people mistakenly assume is that, well, the likelihood of inheriting this is 1/4. So if I have 4 kids, only one of them is going to have it. No, that probability exists for each child. Now, is it more or less likely? It's less likely that all 3 would have it, because it's 1/4 times 1/4 times 1/4. So that probability is 1/64. And if you put that into a decimal form, that's only 1.6% probability for all 3 of them to get it. Okay, it's a 1/4% chance for any child to get it. Okay. Now, if you were going to ask this question from the other way and say, what's the probability that any one of those kids has it? 1 out of 3. Well, it could be the first kid, right? And that answers the question. It could be the second kid. That satisfies the question. It could be the third kid, right? What if the question said at least 1? So if they have 1 kid, any of them, then that satisfies it, right? What if they had 2 kids with constitutive analgesia? Would that also satisfy that question? Yes, it would. What if all 3 of them? Yes, it would, right? So the only way that that question wouldn't be satisfied would be if none of them had it, right? So what you really need to figure out is what's the probability that none of them would have it, right? So if you said at least 1, the opposite of that is none. So what's the probability that none of them would have it? Well, 3/4 of the time they won't have it, right? So 3/4 times 3/4 times 3/4. That's 27/64, I think, right? That's the probability that none of the 3 would have it. So the probability that at least 1 would have it is 1 minus 27/64. So we'll get more into the binomial expansion in a minute. Of course, a dihybrid cross. This is where we really use a fork diagram. If you had a couple of different phenotypes, like droopy ears or crinkly-tailed mice, let's say they're recessive traits, and you had a heterozygous breeding pair of mice. So they have the wild type regular mouse phenotype, but when they have offspring, right, we know that using a fork diagram, we could predict that they're going to have this genotype ratio. And from this, you know, they're going to have a 9:3:3:1 phenotype ratio. They would have 9 that would have dominant alleles, and that would be this one, this one, this one, and that one. So that's 1 plus 2 plus 2 plus 4 of them would carry a genotype that looks like this. They have a dominant droopy, they have regular ears, they have regular tails. And 3/16 of them are going to have regular ears, but they'll have crinkly tails. Which of the genotypes would that be? Would be that one, right? And it would include this one, or these two. So that's the 3. And then it's possible that 3/16 of them would have droopy ears, but regular tails. Which ones are those? Droopy ears, that one. Regular tails, droopy ears, regular tails, and that's 3/16 again. And then it's possible that only 1/16 would have a mutant phenotype for both traits simultaneously, double recessives. That's the bottom one there, right? And so we know we get that by doing our fork diagram, multiplying all of the things by all of the other things. That's because getting this genotype is independent of getting that genotype, or that genotype, or that genotype. So each of those genotypes is inherited independently because of the law of independent assortment, okay? So what's the probability of any of those things? Well, if you look at the phenotype, just the overt phenotype, there you go. What's the probability of being wild type? 9/16. Okay, wild type is a phenotype. What's the probability of being a double homozygous wild type, or dominant? Wild type is the dominant version. What is the probability of being a double homozygous wild type? Not wild type, but a double homozygous genotype wild type. Huh? 10/16? No. Think of the question asking, double homozygous. So that means that both alleles have to be homozygous for both loci.
1/16.
1/16. It's just that one right there. What's the probability of being doubly homozygous recessive? 1/16, right? It's the only phenotype that that genotype can produce, and it's also 1/16 of the genotypes, okay? So what about other questions? What about, where'd it go? What about having either being totally wild type for both traits or totally mutant for both traits? So we're asking, what's the probability of being wild type or mutant? Or mutant. You can't be wild type and mutant at the same time for both traits. So which rule we have to use? The sum rule. And so we're going to add the two probabilities. The probability of being normal is 9/16. The probability of being a double mutant is 1/16. So the probability of being one or the other, if you just reached into the cage and grabbed a mouse, what's the probability you pull out a mouse that is either completely normal or completely mutant? 10/16, okay? Which is 62.5%, okay? So if you reached in there 100 times, you'd 62.5 times, you'd pull out either a completely normal mouse or a completely mutant mouse. What about the other 30, however many times that is, 37.5 times? What are you going to pull out then? What would you call these. Well, these can be heterozygous. Hybrids, okay? So heterozygosity only describes the two alleles at a locus. You can't use that to describe one locus relative to another locus. That would be a hybrid, okay? So because these have a combination that no parent had, then they're hybrids. All right, so what's the probability of getting a hybrid? Well, it's 1 minus the probability of not getting a hybrid, okay? So always think about that. The probability of the other thing or things is always 1 minus. So if you can calculate something easily or more easily, you can always just subtract it from 1 to get the thing that might be more difficult to calculate, because it always has to sum up to a 1, of a total of 1. So here's another one. So what's the probability of a mouse having a genotype that would make it pure breeding? Pure breeding. So first, don't start adding anything. First, remember what that key word means. What does pure breeding mean? Homozygous at all genotype, at all loci, right? So which ones of these are homozygous at both loci? Let's look. Is this one homozygous at both loci? This one? This one? Yes. This one? Nope. 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 Yes. Nope. Yes. Okay. So don't be fooled. Homozygous doesn't mean dominant, doesn't mean recessive, has nothing to do with those two things. What does homozygous mean? Same two alleles. Could be both recessive, could be both dominant. You're like, but this one is dominant and that one's recessive. Who cares? They are the same at that locus. Okay. So it doesn't mean that you have to be all dominant or all recessive. It just means that you have to have homozygosity at every locus. And so what's the likelihood of being a homozygote? 1/4? Okay, that 1, 2, 3, 4. 4 out of 16, or 1/4. Because you can't be two different homozygotes at the same time. So this is another mutual exclusive question. You're either a double dominant, double recessive, hybrid like this, or hybrid like that one up there. You can't be two different genotypes at the same time in the same organism in this instance. So that's a mutual exclusive thing. It's a this or that or that or that. You have 4 ors, 4 choices there, okay? So you just add them all up. 1/16 times 4, that's what you got. So I want to get in a little bit more into this binomial expansion thing. Why is that not? So the binomial expansion equation is there, and your textbook wants to tell you about Pascal's triangle, okay? So you tell your book to go stuff itself, because Pascal's triangle is, it's like the slide rule, and you've got a calculator. Are you going to use a slide rule? No, you've got a calculator. So don't use the old antiquated technique and technology. Use this equation that's much simpler, okay? So don't even read that section on Pascal's triangle in the book. Read these notes and practice the problems using this approach. So for this process, you've got some probability you're trying to figure out, okay? Like a while ago, we were trying to figure out what's the likelihood that any one of the 3 kids might have that disease. Not the first one, or necessarily the second one, or necessarily the third one, but just one out of the 3, any one of the 3, what's the probability, right? Well, there's more than one way that that could happen, right? It could happen because it's the first kid, right? So that's one way, hold up a finger. It could happen because it's actually the second kid. That's a second way. So there's 2 possible ways, right? Or it could happen because it's actually the third kid, right? So there's 3 possible ways. Well, if something has a certain probability, but then there's 3 ways that it could occur, do you think that it would be more likely or less likely that it could happen? More likely, right? You guys ever, what was that movie? It was a while back. I thought it was kind of funny. Was it 101 Ways to Die in the West, or 1001 Ways to Die in the West, or something's kind of funny, kind of dark comedy? But right, if there's 1,000 ways to get killed in the West, is it more likely that you're going to get killed or not get killed, right? Well, so if it's more possible ways for an outcome to occur, then the probability just intuitively should be more likely than just happening once, right? So what's the probability of just the first kid? Well, that would have been 1/4, right? So is it probably going to be a probability that's higher than 25%? That kind of should be an intuitive feel, okay? So that's the probability that we're thinking about. And then you just substitute in all the little things, right? So we're thinking 1 kid, well, that's the number of events that we're interested in. We'll throw that in up here. How many total events? Well, 3 kids. So that goes here. How many of those events are actually the ones we're interested in, or the outcome that we're thinking about? That's 3 minus 1. So that would be a 2. And then what's the probability for the outcome that we're interested in? That would be having the disease. That's P. And that was 1/4, right? What's the probability of not being the thing? Not, in this case, not having that analgesia. 3/4. So that's the Q. So outcome 1 is always, just consider it to be the outcome that you're asking about. And outcome 2, or the Q, are all other outcomes. What if it had more than just 2 phenotypes, but you're still only interested in 1 phenotype? Well, you could just lump all the other phenotypes as being not that, right? I saw a meme yesterday. It was like, remember, everything in the universe is either a duck or not a duck. Is that true? It is true. It's a dichotomy. So it's the same here. Everything you're asking about is the phenotype you're interested in or not the phenotype you're interested in. And that can just be lumped into Q, which would be 1 minus the probability of the thing you're interested in, right? So factorial, you've probably seen that before in one of those fancy math classes you've been taking. Factorial is defined for 0 to be the number 1, and for any other integer, it's defined as all of the integers, including that one below it, multiplied together, right? So 4 factorial is actually 4 times 3 times 2 times 1, or the number 24. Fancy calculators, you've probably got a little button that lets you just push that in, okay? But before you go button pushing and go crazy there, it's always actually better to simplify these equations, because that usually requires less button pushing. So let's talk about this example. We've got some people that have brown eyes, but they know they're heterozygotes. They had a parent that had blue eyes, for example. You'd know you're a heterozygote. They're going to have kids. They want to know how many, or what's the likelihood of some outcomes, like who really cares? But it's a simple genetics question. It's not even 1 gene, so it's totally bullshit, but whatever, we'll go with their game. They're going to have 5 kids. So right off the bat, you can tell they're nuts. And then what's the probability that 2 of them would have blue eyes? Why? You're going to sell them or something? I don't know. Why do you care? Anyway, all these questions are always, you just start thinking deeper about it and you're just like, what? All right, so let's go back and just pretend. So, you know, if you just looked at that, it's a dihybrid, or it's a monohybrid cross again. So 1/4 possibility of being homozygous recessive and having those blue eyes, 3/4 chance of not having blue eyes. So P, the little p becomes 1/4, the little q becomes 3/4 for our equation. Now, how many things are we interested in? Well, we're interested in 2 of them. So that's the number of events, that's X. And well, we reversed it, didn't we? The things that we're interested in are the 2 of the kids, and the total number of events are 5. It doesn't really matter whether you use X or it doesn't matter. As long as you put it in all the right places. All right, so 5 things happening. The ones we care about, X. How many of them aren't of the phenotype we care about? 5 minus 2, that's 3. I left it as 5 minus 2. And then you throw in 1/4 here. And how many are like that? Okay, that's going to be raised to a power. So that's squared, because 2 are going to be like that. X is the same X. How many are not going to be like that? N, it's the same N. So that would be 3, right? And so again, you could press all these buttons, but before you go to pressing buttons, think about simplifying the equation a little bit. You don't really need to multiply 5 times 4 times 3 times 2 times 1, because that's just going to cancel right out from the 3 times 2 times 1. So really it's 5 times 4, which is what? 20 divided by 2, 10, okay? So that's telling us that there are 10 different ways that this could happen. That number in front, that term, that is the number of different ways. And on a Pascal's triangle, although you're never going to go look at this, that would be determined by one of the things across one of the rows. But you'd have to remember what the rule is. I don't even remember what the rule is. I don't want you to know what the rule is. Know this equation, right? This says there's 10 different ways. That's what that solves down to when we add 5 over 2 times 3. So is there really 10 different ways to be that can happen? Because you've got 5 kids, okay, and 2 of them need blue eyes. So one way that can happen would be the first 2, right? So we'll put blue, blue, not blue, not blue, not blue, right? Is there another way? There's supposed to be 10 ways. Can we find them all? Okay. Four of them. Is that all of them? Hey, it was right. What do you know? Math worked. One of those times when you're going to actually use it. So that's 10 different ways to come out with the same outcome. What's the probability of that outcome? Well, it's 2 of them having blue eyes, that's 1/4 squared, and 3 of them not having blue eyes, that's 3/4 cubed, And those numbers are there. So that boils all down to 26%. What was the probability of one of them having that? Just one kid having blue eyes would have been any one kid. 25%. Is 26% more than 25%? Yes. So our gut feeling that it would just be inherently more likely is true. Okay? All right. Now, the more complicated question and much more likely to be asked question is not what's the likelihood of 2 kids having blue eyes, but the likelihood of some number that would include more than one way for that to be answered in the positive. Okay? So more than one possible outcome of multiple possible outcomes. It's like this, they are going to have the same 5 kids, but what's the probability that at least 2 of the kids? Like, isn't that just the same? No, because what if they had 3 kids? So if they had one kid that had blue eyes. So this is the number of blue eyes. They might have one. Does that meet the criteria or not meet the criteria? No. We'll put it. 2 kids have blue eyes. Does that meet the criteria of the question? 3 kids have blue eyes. Does that fit? Oh yeah. 4 kids? Yep. All 5 kids? Yep. So how many different ways are there to get at least 2 kids? 4 different ways to get 2 kids, and we know already there's a 26% chance of getting the 2 kids. So what we have to figure out is, well, what's the likelihood that we actually got 3 kids? What's the likelihood that we actually got 4 kids? What's the likelihood that we get 5 kids? Because if you get only 2 kids, can you get 3 kids? These are mutually exclusive. So you can only satisfy the equation in one of these ways. Either they have just 2 kids with blue eyes, or they have just 3 kids with blue eyes. Or they have 4 kids with blue eyes. But we know that the probability for each one of these is independent of the others, right? But also exclusive from it. So we can say, well, we can't just take those probabilities and just multiply them. That won't work. We have to take those probabilities and add them. So we have to calculate a probability that we get 2 kids, a probability that we get 3 kids, a probability for 4, and we have to add them together to get the actual probability of having at least 2 kids. So we have to do 4 calculations, right? 4 binomial expansions. We have to do a binomial expansion for 2, which we just did. Now we have to do that again, but do it for 3. Do it again, do it for 4, do it again and do it for 5, and then add the results of those 4 separate calculations. Or do it the easy way. What if they had no kids with blue eyes? Let me grab that one. Or what if they had 1 kid with blue eyes? So the probability, if you add all these up, is 1, right? So the probability that they have a kid with at least 2 is 1 minus the probability of not having at least 2. So the probability of this occurring, right? 1 minus the probability of not being 2 is the opposite of at least 2. So we could do 2 calculations. We could calculate the probability that none of them are blue. This could be all brown. Another way of writing this would be to say 0 blue, or that only one is blue. And 1 minus those two calculations would give you the same number as if you took the 2, the 3, the 4, and the 5 calculation and added them together. So sometimes it's worth your effort to think about the question and solve it in the most expedient fashion instead of the most brute force fashion. So rather than summing that all up, you would want to do it something like this, because whenever the expected number is 0, the binomial expansion equation simplifies very fast. Okay, I should write that on here. I didn't. I said to end it. Whatever. All right. Where was I? Here. So whenever you have 0 things, well, we have 5 kids. 0 of them are the way we want, and 5 of them are not the way we want. And the probability of what we want is 1/4, and the probability of what we don't want would be 3/4, right? That's the equation. So 5 factorial times, this is 1, remember? 5 factorial divided by 5 factorial would simplify to 1. 1/4 raised to the 0 power is 1, and 3/4 to the 5th. So anytime X is 0, anytime the number of events you're concerned with is 0, it's just going to be Q to the number of things, right? 2 to the number of events, 2 to the n, sorry. 2 to the n. So if we look at that equation, the probability for 0 blue eyes is 3/4 to the 5th. That's a simple calculator punch. The probability for one of them is given here in this, that equation, which will simplify down because all that cancels out. So it's going to be this equation. I'm just kept these as fractions just to show you, if you're like, I can punch it all in my calculator and get a weird number, check to see if the weird number makes sense. So it'd be 36%, 36.7%. So what's the probability of getting at least 2 kids? Should it be greater than the probability of getting exactly 2 kids? Yeah, because it makes sense, because there's 4 ways to do that, right? And so it makes sense that it would be more likely, and it is, right? What's the probability that all 5 kids would have blue eyes? Do you need to do a binomial expansion? You could do a binomial expansion, right? If you did that, you would say, okay, there's 5 things, and 5 of them are the thing I'm interested in, and 0 of them are the opposite of that, and the probability of the thing I'm interested in is 1/4, and how many are going to be like that? And the probability of not being what I'm interested in is 3/4, and how many are going to be like that? None. So it becomes, right, 1/4 to the 5th. Right? So when it's all the way you want, then it's going to be 1/4. It's going to be your probability of that outcome to the number of children or number of events. Okay. So the all or the 0 are easy to calculate. The all or none are easy to calculate. So anytime you could throw one of them into your equation, that makes it an easier calculation if there's 4 ways to calculate something versus, or 4 calculations to do versus only 2 calculations to do, which way should you go? 2. Go with the 2. You guys in the lab yesterday, remember I said, if there's a shortcut that works, use it. So the binomial expansion is, and I think the questions I asked you to look at in the back of the chapter are binomial expansion questions where you have to figure out the answer of the probability based on using that binomial expansion. So that's why I want to go through it in a little more detail. Okay, so the other type of statistical analysis. So this type of statistical analysis that we've looked at are predictive statistics, or asking like, what's the likelihood of this outcome or that outcome, right? And we've used it as a product rule to say we can find the likelihood of independent events occurring simultaneously. And we can use the binomial expansion version of that to look at independent events happening simultaneously in an unordered way. Okay, so think of this. It's simultaneously having 2 blue-eyed kids, but it's not ordered because it could be any of the 5 in any combination, any order, okay? So binomial is when you're going to be using unordered series of events, okay? And then the sum rule, which is a little bit more or a little bit less likely to come up, but if the 2 things that you're asking about are mutually exclusive and you're trying to create a situation where you're asking about a choice, is it this or that? What's the likelihood, right? Then that would be a product, the sum rule type thing. Now, another statistical analysis that we use is a statistical prediction to ask how well does a set of data match to an expectations for that genetic cross, or an expected set of data. And this type of analysis, there are multiple different versions of this. There are t-tests, that's kind of one. There's 2-tailed and 1-tailed and bob-tailed and ring-tailed and, no, just kidding. And there's the chi-square test. So chi-square, pronounced chi, not chi. That's something different. This has nothing to do with your inner spirit. This is a statistical method. We sometimes call it a goodness of fit. How closely does our observed data match to an expected set or theoretical outcome from a genetic cross? And where does that theoretical or that expected comes from? Well, that comes from using the statistics we just talked about, the independent events. If we did a genetic cross and we said, well, it's likely that 3/4 of them are going to have brown eyes and 1/4 of them are going to have blue eyes. Well, we get a whole bunch of kids and we look at them and we figure out, well, how many have each thing, right? Like if we said, well, a trait that's usually dominant is where you have your left thumb on top, okay? And recessive is your right thumb on top. So in here, we could take a poll, or we could collect the data and observe us all and say how many are right thumb on top and how many are left thumb on top, right? So we take those numbers and we calculate a ratio and we'd say, well, we know it's dominant. So the likelihood in the population is that we should have about 3/4 of the people have the dominant phenotype and about 1/4 having the recessive phenotype. Right? And we'd ask, is that what we saw? We'd want to compare the observation we made in our data to the predicted observation and ask, is it close enough to say, yeah, that prediction makes sense, or that prediction actually predicts reality, or maybe our observation is flawed if we have more faith in the prediction. And so that's where we would use the chi-square, okay? We would use it to support a hypothesis. So if we calculate we observe a population and we calculate or try to deduce that their genotype would be a particular genotype, and we would say, okay, if that is truly the genotype, we could get a hypothetical prediction on what the percentage in the population should be. We expect 9,331 in our phenotypes, but we don't obtain 9,331. Let's say our actual observed ratio is closer to like 8 to 4 to 3 to 0.9. So is that close enough to 9 to 3 to 1 to say that it's the same? What's the likelihood that there is just some inherent error that prevents us from getting that very perfect answer, that very perfect exact ratio we would predict, right? And with statistical analyses, where you're sampling population or you're sampling data or using sample data as your comparative to a theoretical, you always have to take into account your sample size, okay? So the larger a sample size, the more robust the statistical analysis can be and the comparisons can be, right? If you flipped a coin 10 times and it came up 7 heads and 3 tails, would you really think that there's something wacky with the coin or that you were being cheated, right? If it was 7 to 3 out of 10 tosses, you believe it, right? What if you flipped it 1,000 times and it came up 7,000 times heads and only 3,000 times tails? Same percentage, but would you believe it? No, because the sample size has gone up now, okay? So with a larger sample size, you expect the statistical prediction to match more closely to the actual data. So with 1,000 tosses, it would be pretty improbable that you would get 7 to 3 ratio. Now, 593 to 407, would you believe that? I'd believe that. That's pretty close to 50-50, right? So you think, okay, I'm supposed to be getting like 50-50 and I'm not, so something's wacky, right? Well, did you have a lot or did you just have like 2 tosses, right? If you flipped it twice and you got 2 heads, oh, that's a loaded coin, right? No, it's not a high enough statistical sample. So the general formula for this is to take our observed values, our observed phenotype ratios, or whatever we're counting, actual numbers, whatever it is, subtract our expected values from that, square that result, and divide it by the expected value. This is basically creating an how far away is your observed from the expected. Now, you might have multiple different observational classes. In genetics, we generally are. You're going to look for maybe 4 phenotypes or 6 phenotypes or 8 phenotypes simultaneously. So for each individual phenotype you have, or for each observed data that you have, you're going to have one of these terms. And the overall value is got by summing those terms. So if you had a situation like this where you have 2 genes, you expect them to be independently assorting because of Mendel's rules. So you expect, well, I should have a gene that affects wings, and the normal wing is dominant to a curved wing. The normal body color is dominant to the darker body color. And if you did a cross where you took a wild type animal and you mated it with a mutant animal, that would be your parental cross, right? And these are fruit flies or something. And then you look at the F1 generation and you see that they are all heterozygotes. So they all have wild type phenotypes, but then you let them mate with each other so that the F2 generation is formed. And when you look at the F2 generation, you look at a total of 352 individuals. And of those, you have 4 different phenotype classes because you're looking at both traits simultaneously. And you would predict a 9 to 3 to 3 to 1 ratio, right? Okay, just substitute in different symbols here. And you would predict that would actually be this, using the symbols that we've used. Is it curly? So you would predict that there'd be very few that are totally mutant. You'd predict a lot of them are going to be wild type, and there'd be some hybrids, about equal numbers of the two different groups of hybrids. But this is the numbers you actually get. So you would say, well, if I had 352 flies and I expect 9/16 of them to be like this one, right? I would take this and multiply it by 9/16, right? If I have that, I would expect 1/16 of them should have this, right? So what's the expected number that I would have? This is observed. How would I calculate that? Here's a shortcut. Take this number, somebody whip out a calculator and do it right quick. Take this number and divide it by 16 and tell me what you get. Say it louder. Multiply that by 3.
22.
3 times 22 would be 66, right? Multiply that by 3. I'm going to need a calculator help on that one.
198.
So the expected numbers, right, would be 198, 66, 66, 22. And our observed numbers are close to, but not identical to, those values. So we need to apply our chi-square test, right? So, oh, I had it. So there it is. But wasn't it more fun to do it that way? All right, so there it is. There's your expected, okay? And there's 4 things. So we're going to have 4 of those different, 4 of these different terms, right? So plugging everything in, and it really doesn't matter which number you subtract from which number. A lot of people get hung up on that. It doesn't matter because it's squared, but it does matter which number you put on the bottom. The expected has to go on the bottom. So you can take all those, do the math, you get 4 separate little results, add them all together, and you get a chi-square value. And so what is that magic number? Chi-squared value is, that's the Greek letter chi, lowercase. That value is a measure of variance, okay? It's a measure of variance. How much variance is there between the observed data that you have and the expected data that you calculated? And the question we really want to answer is, what's the likelihood that that much variance would exist? Okay, so it's a variance. It's really an amount of variance, right? It's 1.06 variance, whatever there's no units, but pretend there's units. It's 1.06 variances. So is that a lot? Should I expect that? Is that reasonable? Is that way not reasonable? Right? So the more things that are happening in the process, the more variance might be expected to occur. So we have ourselves some leeway. This thing has 4 different phenotypes that we've got to calculate or tabulate and observe. So there's a little bit of complicatedness to the process right off the bat, right? So what we do is we take our chi-square value and we want to look for the likelihood that that amount of variance would occur. We have a table of probabilities. So this is called a probability table. There's one in your lab manual, and you can always use that one. And if you ever need one on a test or something, I put it on there. So we have the first thing to think about here is the degrees of freedom. Okay, so poor man's definition, how complicated was the set of observations? If the observations are more complicated, you need more degrees of freedom, a little more wiggle room in how well your data match to the expectations, right? If something's a little more complicated, you get a little bit more play as to whether you have to match it really close. Your chi-square value is going to be a measure of how close you were. And the probability of that amount of closeness is given to us by the top row of probabilities. So in that example we just did, we had 4 phenotypes. So how complicated was that experiment? Well, we have a rule. We say however many phenotypes you observe, or categories you observe, you get that number minus 1 degrees of freedom. So we give you that a little bit of slack. So we would look for 3 degrees of freedom because we had 4 observed phenotypes. And if we look at that 3 degrees of freedom, we then want to go look for our chi-square value, which was 1.06. So where is it? Well, there isn't a 1.06, there's a 1.005, but 1.06 is bigger than that, but it's not that big. So the exact chi-square value you tabulate is probably not going to be present on most tables because there's essentially an infinite number of chi-square values, and you aren't going to draw a table with an infinite number of values on it. So our chi-square value is somewhere there, right? So what that means is the likelihood of that amount of variance, that's the amount of variance we saw, how likely is it that that would occur? Somewhere between 50 and 80%, actually a lot closer to 80%. If on a more refined table that had some additional values in here, right? This is sort of like the old human version of counting, right? 1, 2, lots. Okay, so they went 50, 99, 95, 80, and then they just dropped off. They kind of, where's the 70? Why not 75? Maybe this is 79, who knows? All we can tell from our table is it's somewhere between 50 and 80. So the probability is somewhere between 50 and 80% that that amount of variation would occur. You'd kind of expect it. And is that okay? Well, we need another rule. What level of probability is okay? How much variance can we live with and still say, there's really not much difference? Well, we give ourselves a lot of room, wiggle room. In genetics, anything on this side, anything above 5%, that's 5%, anything 5% or above, we go good to go, right? You're like, my data only matched the observation with the probability of 5.1% likelihood that it matches. Golden. Okay? That's that, in most of the world, in most things, that's not going to cut it, right? It's like, I successfully performed appendicitis operations 5% of the time, right? You're like the guy on the commercial where it's like, is this really good enough? Is okay good enough? Well, it is in genetics, okay? It is for this type of analysis. So chi-square is something we'll apply to data that we're going to be playing with in lab that you guys got to play with yesterday, that some more of you will play with today. We'll apply it to something, okay?
Will these examples be on D2L?
What was the what?
Will these examples be online on D2L?
Yes. Yeah, I've been just deleting the other slides and putting the slides that I wrote on.
Okay.